So what we're going to talk about today is we're going to talk about dead stars, okay? We're going to talk about dead stars. And if you watch the video, the last couple of videos, they talked about how stars went through their life cycle and died, but I didn't talk about what the dead stars themselves were like. And by the way, there is a fancier term for dead stars, okay? It's called stellar corpses, okay? Stellar corpses, like a corpse is a dead body. So a stellar corpse is a dead star, okay? So it's kind of we're getting goth in here. Yes, we're going grim and edgy, okay? Now, so let's talk about dead stars. First off, if you watched the videos last time, do stars like our sun explode? Okay, will our sun explode in a supernova one day? Yes or no? See if anybody watched the last couple videos. No, that's correct. That's correct. Stars like our sun are not big enough, they're not massive enough to have a supernova explosion, okay? But they will die in something that, if you didn't see it happen, might look somewhat similar. And you can see one right here. So this right here, this is a planetary nebula, okay? And remember, if you watch the videos, I don't like that name because this has nothing to do with planets. Planetary nebulae have nothing to do with planets. All this is a star like our sun will slowly puff itself to death. When it runs out of fuel, it will slowly, over a few thousand years, just release gas. And as you can see here, the star used to be right in the middle of this picture, and stuff is just sent out in every direction, okay? And if you want to see how that happens, watch the last couple of videos. Now, check this out. Almost all of the material flies away, okay? Almost all of the material flies away. What is the only part of the star that would be left behind, probably? If you had to guess, what part of the star would be most likely to be left behind when most of the stuff flew away? Which part? The core. That's correct. It would be the core. The core is the densest part of the star, and it's already in the middle, right? So everything essentially flies off from the core. A little bit of the other material will stay, but it's mostly core, okay? And so, let's think about this. Compared to the original star, how big is this leftover piece going to be? I don't need an exact amount. If you compare the size of this leftover core to the original star, yeah, it's going to be much smaller, okay? So it's going to be very, very, very small, right? And until the stuff flew away, it was the core of the star. So what is its temperature probably like? What's the temperature of this leftover core going to be like? At least initially. Really hot or really cold? Hot, right? When we talked about the sun, we talked about how the core was the hottest part of the sun. So if you suddenly reveal that core, it's still going to be pretty hot because a couple thousand years is not very much time. That core has not had a chance to cool off. So that means that the surface of this new dead star will actually be hotter than the original surface of the star it came from, at least initially. Okay? And again, that's where this kind of star is going to get its name. It's very, 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 very hot. So what color is it going to be? What color do we associate with very, 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 very hot? A whitish blue. You guys both, a whitish blue color. A whitish blue color. We got both parts there. It'll be a little bit bluish, but it'll be giving off enough of the wavelengths that to your eyes it would look white. So it's very, very small, and it's very, very whitish blue. Does anybody know what this kind of dead star is going to be called? its name comes from those properties. What type of dead star are we probably talking about right now? Oops, got some technical difficulties. Yes, what we're talking about right now is called a white dwarf, okay? It's called a white dwarf. So that's the first type of stellar corpse, or the first type of dead star. This is the kind of dead star that our sun will leave behind when it goes through this planetary nebula process. So let's talk about what white dwarfs are. And first of all, let me go ahead and show you what a picture of a white dwarf real quick. Let me get it on here. Here you go. Here's a picture of a white dwarf. But not this. That's a regular star. Actually, a white dwarf is... Oh, this is right there. Oh, there's the white dwarf. Oh, such a nice little... Oh, such a cute little white dwarf right there. So, what are white dwarfs like? Okay, now, here we get to this. Why do we consider this to be a dead star specifically? It's because the process that causes our sun to glow right now, the process that produces the light of our sun, is no longer working in a white dwarf or in any dead star. And somebody's saying it right now in the chat. No fusion, okay? Basically, a white dwarf, like all dead stars, has run out of the kinds of fuel that it can use to continue to fuse, okay? So once fusion completely stops in a star, it's considered dead, okay? All right. Now, if you watch the last couple of videos, remember, fusion was a process that was happening towards the core of a star and would push outward, okay? Now, inside of a star, there's also a force that tries to crush the star. What force would that be? What force would be trying to crush the star? And this is the same force that tries to crush anything, basically. Gravity, right? Gravity. So we say, if you watch the video, I constantly was mentioning gravity crushing stars and fusion fighting that gravity. And if they're exactly equal in strength, then the star stays one size. If gravity was winning, if the gravity was stronger than the outward pressure from fusion, what would happen to the size of the star? If gravity was stronger than fusion, what would happen to the size of the star? Would it get smaller or bigger if gravity was winning? It would get smaller because gravity's trying to crush, right? So if gravity is winning, it crushes. And if you were in a stage where fusion was winning, then the star would grow, okay? And so throughout a star's entire life, it's just a back and forth between those two processes. Gravity shrinking the star and fusion trying to grow the star. But here, what's happened to the fusion? We said it turned off. So who's going to win in the white dwarf? If the fusion is totally turned off, who's going to win? Well, it's got to be gravity, right? It's got to be gravity. Yeah, it's got to be gravity. And therefore, what would we expect to happen to the size of the white dwarf if gravity is winning? Let's put it all together. If gravity is completely winning in this dead star, we expect it to shrink, okay? So white dwarfs are actually smaller than the core that they came from, okay? White dwarfs are going to continue to shrink until they get to be about Earth-sized. And remember, is Earth a very big planet? No, right? Earth is a pretty small planet. So these white dwarfs are very, very small. They're the size of terrestrial planets, okay? But here's the thing. Once they crush down to about Earth size, they stop shrinking. Does that mean that gravity gave up? Yes or no? If the star stopped shrinking, does that mean that gravity got satisfied? Gravity was like, good enough. I quit. No, because when does gravity quit? When does gravity quit? Gravity never quits. Gravity never quits, right? It never ever quits. It's never satisfied. It's just, it always wants. It takes and takes and takes, right? So if gravity is still trying to crush it, why does it stop crushing? Well, something else must be fighting that gravity. It's not fusion, because it's a dead star. There'll never be fusion again. So what's fighting that gravity? Now, what's fighting that gravity in a white dwarf is confusing. It's very weird, okay? It's very strange. And it's something that comes to us from quantum physics, okay? We haven't had to talk about this too much before, but we're going to talk about some quantum physics real quick, okay? And you probably have only seen quantum physics mentioned in like sci-fi movies, and that's okay. I don't expect experts on quantum physics. So, do you guys know what quantum physics actually studies? Anybody know what kind of stuff quantum physics is about? I just keep saying quantum physics. It almost seems like a meaningless word at this point. I really don't expect anybody to really know. That's okay. Well, in a way, so somebody said it studies how the universe works, how stuff works. In a way, I would say yes. I would say that's true, how stuff works. But specifically, quantum physics, frequently what it's studying is microscopic particles, okay? Like, it explains how particles work. It's not the only thing it studies, but it's one of the big things, right? And why is that important now? Well, I mean, Earth size is not microscopic, right? But it's made out of particles, right? It's made out of particles. So let's kind of think about what kind of stuff it would be made out of. And this, if you don't quite remember everything from the last couple of videos, you might not be able to get. So I'll just go ahead and say this. The core of this star, before it died, the reason that it died is that this kind of star, like our sun, when it uses up all of its hydrogen and its helium in the core, it ends up with carbon and oxygen in there, okay? So that core, that dead star, is going to have a lot of carbon atoms, it's going to have a lot of oxygen atoms, and it'll still have a lot of hydrogen and helium mixed in that didn't get released.